an interesting topic of classifying surfaces, or rather different locations of surfaces. We can see already a couple of interesting ones is saddle point and extreme points, minimum or maximum, and there is a generic point. So there are probably a few like this, and then generically the surface is when zoomed in is a plane. Okay, so this is also a plane, but it is a horizontal plane, and around the horizontal planes the behavior might be, as you can see, quite weird, and it is a saddle point. So if you want to be careful with this saddle point, you would plot, say, in different color to indicate, as I did last time, different levels. Okay, so and it could go up. Could go up in this direction and down in those two directions. So that certainly is to be taken into account. Then what we discussed is this topic, and that is apparently there is some worth discussing is implicit curves. So implicit curves, and as opposed to explicit curves, implicit curves is another good way to put it. They are implicit relations. So all of these are implicit relations between x and y. So you do not plot them as graphs of functions. You plot graphs of functions, you plug in x, you make a table just the way I did over there, and for each x, you plot y. Okay, you have a function y equal x squared. Whether it is a parametric curve function, several variables, or calculus 1, numerical functions, that's how it works out, and then you plot it one by one, and so on. Okay? With implicit curves as these, you certainly could try to use that approach, but it will be, you have to split the graph into several, and so if you don't want to do that, it probably becomes quite a challenging one, because you have x's and y's, and then what you're supposed to do is you think of several pairs xy, say 1 and 1. Okay, say I'm talking about maybe this one. Okay, 1 and 1, and then I compute x squared plus y squared, which is 1, and then I compare it, which is 2, and then I compare it to the value of what it's supposed to be equal to 1, say 1. Okay, and then since it is 2, then the answer is no. And so what would I have accomplished is one little thing, and that is that this is not a point on the graph of the function. So I keep moving, and then, so for example, if I try 0, 1, and they adapt to 1, then it is okay. That point is on the graph, and then I plot it. And then I try 1, 0, and once again I adapt to 0, squares. Once again it checks out, I plot that point. And so trial and error, I go like this on the grid, checking out points, and verifying whether or not the condition is satisfied. So as you can see, the difference is quite large when we're talking about implicit relations. So relation is there, but because it's implicit, it's hard to get a grip off, and then a grip off on it, and that's why we study functions so much easier. But unfortunately, we cannot entirely escape implicit relations. As you can see, that's what happens. All we do is we started with this curve, or with this surface, and then we try to study it without actually jumping to plotting. And so we did level curves. We cut them with, we restricted its range. So these are the values of the range or image of the function, so 0, 1, 2, 3, and then we immediately ended up with a bunch of implicit relations. Each of them can only be plotted in that fashion, unfortunately. So that's what we can do is, with those, is pretty much recognizing them as something familiar. So that is, and then that's why it pays off to do it in advance. So we recognize them as circles. Okay, so we know these as circles, and that's why, and then we plot these circles. We roughly, and then it roughly gives us the idea of what the surface looks like. Because see what I did here. So I took these circles and then lifted them according to the corresponding value of z, and then they form some kind of couple. Okay, so then you can confirm that. So this is the top one. Top one, and the rest are lower, like this. Okay, so some kind of couple. So let me go back to Excel with this and show this particular surface. That's the one. Okay, so you can check the formula. As you can see, ignore the first number is just a coefficient, and then as you can see, the red one is y, the purple one is x, and so y squared plus x squared is the surface. So the surface is plotted here, as you can see, because does not show the surface in the shape of a bowl, but it's only because the domain is restricted to a square, okay, or a rectangle, and that's why you have these flaps. But you can see the level curves are visible, right? So those curves are, well, actually, with the question, let me ask you, what's the meaning of the red band? Sure if let me try to, maybe I'll just look at it appropriately if I rotate it the right way. Okay, so if I rotate it, so no guesses. So I want to okay, you seeing it? A little bit dark, but this is the red that I was talking about. So what's the meaning of the red band?
All the points in that section of Z.
That's right. That's right. So in other words, we are restricting the domain again, but not to a single value of Z, but to a whole band. So this is the values of Z that I allow to have, and then the result is not a curve but rather a band. This is another band. Okay, so they certainly vary in shape. Okay, so and over here I plotted those curves that don't have a special name, unfortunately. Those curves that you acquire by cutting through with vertical planes. So these are the ones. So x equal a is incidentally x equal a is an equation of another plane, a vertical plane, and that vertical plane cuts through this surface, and not horizontally but vertically, and the result is kind of some kind of parabolas, right? So in fact I can show you what this is. Look at yeah, okay, see? So this is the data. You can see it's highlighted as the data where the top curve came from. It is so the value of y varies. The value of y varies, and the value of x is fixed at 2. Okay, so that's where that curve is. I highlighted it, and then if I pick this one, okay, so it's the same thing. Once again, the value of y varies, and the value of x is fixed at -1. Okay. Hold on a second. Am I doing the right one? Yeah, it is the right one. Okay, so that's roughly how it works. One more. It looks once again as what does it look like?
It's a saddle.
What?
It's a saddle.
Oh, it's once again a saddle point or hyperbolic paraboloid. You can see the hyperbolas. You can also see those two axes, but the formula is very different, as well as those curves are very different. This for the simple reason because there is a rotation. They simply rotated. The one we started with is z equal xy, produced exactly the same picture here, but very different over there. Well, actually, it's here somewhere. Here it is. So this is xy we started with, right? And as you can see, the saddle point. And these are the cuts by the vertical planes, and they're all straight lines. You remember Pringles made of straight lines, but this one is not the same. It doesn't seem like it's made of Pringles, but it's the same exact surface. It's a hyperbolic paraboloid. And the equation is over here. It is y squared minus x squared. Okay, y squared minus x squared produces the same result, even though it's seemingly different different curves. So So f of xy equal y squared minus x squared. So far, all of these curves that I have, or the surfaces I plotted, are quadratic. So these are what quadratic surfaces look like. They're pretty much what are they? They're either hyperbolic paraboloids, or this one also has a special name. This one is a paraboloid of revolution. So this one is simply take this one of those parabolas, or not any parabola, but take the bottom one. The bottom parabola is this. So as you can see, it is x varies and y varies, and the x value is fixed at 0. So it is the one, the parabola that is very bottom. And you take that parabola, rotate, and you're going to get this surface. Okay. So we have planes and we have quadratic surfaces. What is clearly not here is the sphere. The sphere is not here. Why not? Because it does not satisfy the work-filling test. And so if you want to express it in a similar fashion, you'd have to do, and you don't want to do implicit, which we're going to do in just a minute, then you have to do parametric curves, parametric surfaces. So what I want to do now is jump to functions of three variables, and let's have a little bit of a couple of examples. So, so if what we just saw, the paraboloid of revolution was f of xy is equal to x squared plus y squared. Paraboloid of revolution. So the value of z can be indefinitely, cannot be negative, but otherwise it grows vertically. So we could do something very different and say u is the output variable, and now we have then our function has three variables, and what if this is my function? So on the surface it looks similar to the paraboloid, but the formula, that is, but in reality is, well, where is u? X, y, and z, we can still choose them to be in our three-dimensional space. Okay, but this time, this is the total space of inputs. So there is no room for the fourth dimension for the outputs. So what do you do? We already have an idea. How do we study? We can study a number of ways algebraically. That's ultimately where we end up. But it's still four-dimensional, so there is a little bit of a chance for us to study this. Try to visualize this, whatever that is. So the idea is that we have explored what would you do with studies.
We could fix, say z.
Yeah, we could. That's right, and I would start with z probably. So if I say fix z at 0, then I end up with u equal f of xy 0 equal to x squared plus y squared. So then we end up with a function of two variables. Unfortunately, you see the problem. Unfortunately, these three variables, we end up with three variables, x, y, and z, but x, y, and u, unfortunately, there is no, u still has no room to be plotted. Okay, so in my three-dimensional space, I cannot really say what it looks like unless I actually instead consider the, as I said, the fourth dimension, put it here and study it in that fashion. I don't want to go in that direction. I would rather go in the opposite in the direction that we did the most recently, and that is fixing not an independent variable as we just did. So this is an independent variable. There are three of them, and any one of them can be fixed. But let's fix the dependent variable. There's only one of them, and it does not belong to, it's the one, the most problematic one, because it lies outside of our three-dimensional space. So instead of fix u, say equal to 1. Okay, so then what I end up with is 1 equal to x squared plus y squared plus z squared. Okay, so what are we looking at?
Sphere of radius 1.
It is a sphere radius 1. Okay, so this is the analog of what? For functions of two variables. So this function of three variables, when we fix the function of a value of the output value of the function of two variables, we call them level curves. So this is what? What would you call it?
Level surface.
A level surface, yes. So once again, there is no level literally because those levels go in the direction of u, which faces in the fourth dimension. We can't see it. But otherwise, we can at least plot it, and that gives us the idea of what our function behaves like. So we have a sphere of radius 1, and then we know that on this sphere, what do we know about f? On this sphere is equal to 1. Okay? So then you see where do we proceed from this? We still fix u, but this time we pick a different one, say how about 4? Okay? Then I have 4 equal x squared plus y squared plus z squared, which is what? Well, radius 2. Of radius 2. So I could try to plot it separately, or I could plot it on top of this one. It's a little bit of a challenge, but I'll try. Like this. What the hell happened? Okay, let's undo this. Okay, so the sphere with the same center, right? It will contain our blue sphere inside of it, like this. Okay, and on this sphere, the value of our function is equal to 4. Okay, so you see the point now, what's happening? We're going to do it for every value of z. I started with 1, then a 4, the next one will be, I fix it 9, which gives me a sphere of radius 3, even a bigger one, like this. And so we'll have a family of concentric spheres. Okay, and so once that's the only way to visualize a function of three variables is to plot their level surfaces, which happen to be in the three-dimensional space. And then you know that what's happening here is that the function increases as we move away from the origin, which origin itself is also a level surface, even though degenerate. If I plug in value of u equal to 0, I will end up with just 1 point, and that's how you visualize surfaces. Functions of three variables, and there are certainly applications. That's certainly not made up. You can think of function of three variables in real life. How about temperature? Right, the temperature is in three-dimensional space. It varies in all directions, and hypothetically, if a function like this is like that, it represents then u is the temperature, x, y, z is the coordinate, and so at the location x, y, z, u f of x, y, z is the temperature at that location. Okay, so and then what we're looking at is the temperature growing as we move away from the origin. So temperature, pressure, anything that might be three-dimensional would apply. In fact, all kinds of forces, So even here, we just saw it. Where is it? Remember this one? The function that represents the magnitude of the force of gravity that acts on an object, and so as it declines, you're moving away from the sun, and the gravity becomes smaller and smaller. So if you forget that the force is in fact a vector, and we have, for now, then its magnitude is diminishing, and that's the original statement of the, or at least a part of the law of gravity of Newton. And then that's another one. I mean, this is, I'm sorry, so this is a two-dimensional version, right? It's a two-dimensional version of the law of gravity, even though we know that the space is three-dimensional. So same function, but will be defined on a three-dimensional domain, okay? And so you can imagine what it's going to look like. Well, it's hard, but so what does it look like? How would you, if you take the law of gravity, three-dimensional, what would its visualization be?
Would it just be like, the graphs would still in a sense be concentric, it would just be like stretching?
Right, so they will be spheres, right? So only the distance matters, right? Only for gravity. So once again the level surfaces will be spheres. The one thing I want to actually point out here that maybe I shouldn't have done is I for convenience I picked 4 here to see sphere radius 2, but actually it is kind of diminishes the how well we are visualizing things, because the density of those spheres matters. So in fact, you'd rather do z's at equal intervals in order to see whether or not the spheres become denser or not. Okay, so as I did last time. So for example, I put 2 here, then it will be sphere radius 2, and then when I put 3 here, it will be a sphere radius squared of 3. So as you can see, and but they correspond to values of u that grows in equal intervals of 1, increments of 1. Okay, so which means that with what I had yesterday, I believe, I had circles instead of spheres, but you can see how they become denser and denser with this function. They become denser and denser, as well as with that function. The spheres, the level surfaces become denser and denser as you move away from the origin, but it will be exact opposite with the gravity, because the changes become negligible. So in fact, you simply won't plot it, and there won't be anything to plot. Just like here, beyond a certain point, the change is so small that this kind of approach of fixing the value of the output variable will not be detectable. Okay, so, but the idea is still the same. So these will be spheres, expanding spheres. And well, there is one more picture which is slightly prettier than what I plotted. Just how to visualize functions of 3 variables. Here it is. Okay. So the same thing, but just done not by hand, but by copy and paste, pretty much. So I did Excel, plotted the surface, and then what I did, I just shifted it slightly and then copied over the previous one. But these are level surfaces of a certain function. Okay, and that is we still are able to visualize somehow with difficulty, but visualize functions of 3 variables. Beyond 3 variables, we really out of ideas and out of dimensions. Okay, so that certainly is important, but I hope the lesson is really not how to visualize these functions, but rather the main lesson is how difficult it becomes, and we are going. That's why we study. We do more algebra, and the algebra becomes more important as we progress with dimensions, and there are more parameters, more dimensions, more difficulty, and virtually impossible to visualize. And but we do want to study this because these transition of it does sort of give you some intuition of how what functions behave like, especially as you move from dimension 1 to 2, from 2 to 3, you see how things become more complicated. In fact, it's fair to ask. So this is three variables, okay? Function of three variables visualized like this, surfaces, okay? Just a minute ago, function of two variables visualized by its level curves, okay? What about one variable? Function of one variable, what are the level points? That's right. So when you start limiting your single variable y, the output, and so you cut it with vertical lines, you will have a point, maybe several points, but maybe just a single point. And so that's the difficulty, increase of difficulty. Just one value of the output parameter might produce point in calculus 1, so we didn't even talk about it. Then implicit curve for function of two variables, implicit surface of function of two variables, of three variables, and so on. Okay, so and then we pretty much run out of ideas. Okay, so there's certainly we'll revisit this because the main idea actually is well, there are many ideas it appears, but it is a reductionist idea of reducing the more complex problem, more multidimensional problem to lower dimensional problems. So as you can see, function of three variables replaced with something which is four-dimensional graph. Graph is four-dimensional. Here it is replaced with many, but surfaces, each of which is a surface. So that is the hope is that we can handle those. Well, actually we can. We're just learning how to handle surfaces. But certainly this one is applicable, right? We know how to handle curves more or less, either by functions or implicit differentiation. Remember that, or as parameter curves. So function of two variables, a surface. We try how to understand surfaces. That's how one of the ways to understand it. Okay, so now closer to calculus, or towards calculus, we understand the purpose of calculus, I hope, which is what we started with, and that is the rate of change in, we're talking about functions of many variables, in particular directions, how fast it is changing, whether instantaneously, yes, but initially just incrementally. And that's what planes are for. So they might be approximate your surface in a certain location. You could, if you imagine surface replaced, well, maybe we can actually see it. Well, if you zoom in, can you see it? That's what Excel does, after all. They don't really have a choice. They don't try to smooth it out. But you can see the surface comes as data, as these points. It plots it and then tries to connect it to the surface, and you can see that it actually makes a little triangles. Or triangles, some of them are rectangles possibly, but mostly triangles. So that is the idea of approximation, and each of these is a piece of a plane. Okay, and with the planes, we understand what they do in terms of slopes. Okay, slopes in different directions. So we get to that, but how do we get there? To instantaneous and tangent planes is through limits. So then that's what we are going to be doing now. It is limits. So limits of functions of several variables. Okay, so I want you to look at limits as a whole rather than separate ideas in separate settings. And the setting is, once again, numerical functions of calculus 1, y equal f of x, and then what we just have finished, well, not finished, but at least made progress with parameter curves. So as I put it, was x or p, whatever. I try to use capitals for anything multidimensional. Okay, so t is lowercase. It is a scalar, a number, and the function itself, the output are possibly multidimensional. Okay, and now we are in yet a new setting of functions of several variables. So, and I could write it as I did, was say u equal f of x. So once again, that capitalized x indicates a variable which might be multidimensional, either a point or a vector in multidimensional space. Okay, so as you can see, the complexity grows, but in a different place in these two settings. Either the complex multidimensionality is either in the output or it is in the input, and that's the difference. But otherwise, the difference really is our study of multidimensional spaces. It applies equally to both of them. So, but what is the limit? We will use words first, as we did in Calculus 1. So, how should I put it? Y, f of x goes to L as x goes to A. Okay, so that was the describing the limit with symbols, or you can say that you replace both of these arrows with the word approach. So the input x approaches particular value of A, and then it forces the output y to approach another value. Okay, so if you keep talking about values and inputs, outputs, and you never say a number, then whatever we have to say will be applicable to these two situations. So with parametric curves, it was the input was the same. It was a number, so it was f of t goes to L. Let me put it capital here because it was a vector as x as t approaches A. Okay, and now we flip everything for functions of similar variables. The dimensionality that is. So u is equal to f of x approaches L. Let me make a little L here in order to emphasize that we're talking about numbers. Okay, as x capital is approaching some multidimensional point in the multidimensional space. So then here x in Rn, and while u is a real number, and here x is in Rn as well. Okay, so then the part that needs to be discussed is just the same as the splits into two statements. And the one part is numerical, it is familiar, and the other part is multidimensional. So this is numerical, and this one is multidimensional. So this is might be Rn. So we just need to understand what it means for a point to approach another point in multidimensional space. Then we know the answer is, well, what does it mean? So x, let's speak of sequences, it's simpler. So xn approaches A in Rn, what does it mean? If you remember?
It means that each of the components approaches the component.
That's fine, but I prefer to think about it as a consequence of a definition which does not rely on the components or coordinates or Cartesian system.
Sorry, it's the magnitude of the difference?
Right. Either magnitude, if it is vectors, you speak of, then you say xn minus A approaches 0, or if you only want to deal with distances, in the case when you were talking about points, then it will be simply dxna approaches 0. Okay, either way are equally applicable. Either you think of xn and A as two vectors and you subtract and you compute the magnitude of that vector, or you just compute the difference between these 2 points, which is exactly the same thing. So we'll talk about that after the test, meaning Monday.